There we go. How's that? There's standby mode, apparently. I'm Elizabeth Cooper, the director of the Integrated Design Lab, and most of you are familiar faces. There's some folks online, though, so for them, I will briefly, just an introduction to the lab. This is our current group. The lab is dedicated to the development of high-performance buildings in response to the 2030 challenge and those milestones. So energy modeling, daylighting, those sorts of research areas and outreach and education is what we focus on. A mixture of mechanical engineering staff and students, as well as architecture staff and students. A good group. This program, the BSUG, as well as several others, are sponsored through generous support of Idaho Power Company. They have their newly branded and designed commercial and industrial energy efficiency program. I encourage those of you who haven't checked it out to look online at the possibilities. There's support and incentives there for commercial retrofits and custom projects, so definitely worth checking out. Another project that they have sponsored is the Building Metrics Labeling, which is our online benchmarking tool. Again, a free tool for people to download PDF files that will compare EUI, the Energy Star, Portfolio Manager Score, walkability, and daylighting are all options that you can compare for your project. Obviously, you need the energy data to do that, but a fun tool and worth checking out. The other thing that we offer is our tool loan library. We have at this point over 900 individual tools for measuring everything from power and energy to sound, temperature, the thermal environment, as well as the visual environment, daylighting and lighting. So anybody in the Idaho Power Territory can borrow tools for free. We also have some books and manuals available as well. So for your next project, come check it out and see what we've got. So this is also part of the Idaho Power program and BSUG. The next known topic, I've got one between November and now, which I'm sort of finalizing, but is going to be in conjunction with ASHRAE Idaho's meeting in November. We've asked ASHRAE Distinguished Lecturer Dennis Knight to come out and give a presentation on building performance analysis for building performance rating systems. So looking at your LEED or Green Globes or other rating systems and how energy modeling fits into that. So I think it's going to be a great presentation. That one will be at Idaho Power, and I think that's a Tuesday in November. I think that's when they meet. So, and as always, those of you who are regular attendees have the opportunity to sort of win prizes at the end. So keep coming, keep participating. We'd love to see you. And today's speaker, David Bradley, who is here from Madison, Wisconsin. He works for Thermal Energy System Specialist. TESS is much easier. He received his Bachelor of Science from Swarthmore College and his Master of Science in Mechanical Engineering from UW-Madison. He's also sort of divides his time at TESS between energy simulation consulting work as well as energy simulation or energy modeling software development. He told me he has done energy modeling for the Sultan of Oman, right? Yeah, so that's pretty exciting. Also spent some time on the beaches of Nice, doing fun stuff down there. So I'm sure that you will enjoy his presentation today on eHarmony for energy modeling. And I'd just like to welcome David Bradley. So.
Perfect. Thank you very much, and thank you all for being here. as Dr. Cooper said, I split my time sort of between research and practice, and that's proven to be a very interesting and rewarding place to be. At least I can pretend in front of practitioners that I'm an academic, and that I can pretend in front of academics that I'm a practitioner, and keep everybody somewhat fooled. But in the trajectory of work that my colleagues and I have done, as with every career, we've had some real wins in our book, and we've had some real losses in our book. And I think in conferences we tend to talk about our wins and not talk too much about the losses. And so when Dr. Cooper asked me to give a talk and gave me comparatively little direction as to what she wanted me to talk about, I thought, well, maybe this is an opportunity to talk about, with perhaps a little bit more honesty, about how some of our experiences with projects, take a look at why they did well, take a look at some projects that didn't go so well, and talk a little bit about that too. So I hope you find it interesting and enlightening, even amusing would be good. By all means, if you have any questions as we're going along, please don't hesitate to ask. And I do apologize. I tried to sort of find some balance between talking to people who have a strong engineering background, people who have a strong architectural background, and people who may have a stronger academic background. So I hope that the level of detail is, well, it'll probably displease everybody. That will probably be the end result. But please, by all means, ask for more detail if you, if I'm either being too specific or not specific enough. So, taking a step back, and I'm speaking a little bit here from the software developer point of view. When you sit down and try and create a model of a physical process, whatever the physical process may be, whether it's energy or chemistry or social behavior, math is too hard to solve with all of the chaos of real life. So we have to make a lot of simplifying assumptions. We're going to simplify it down to some math problem that we or computers can actually solve. And when you're developing a piece of software, you've got the ability to build assumptions into the tool, or you've got the ability to sort of pass the buck and let the user at the other end of the line provide you with the values that provide you with more information. So either you build in more information or you ask the user to provide you with more information. And there's sort of levels of assumptions that I'm talking about here. I'm talking specifically about, in this particular instance, about the assumptions that a software developer will build into the model. Not necessarily about the assumptions that software users are able to have access to within the given tool that they're trying to use, although that's important as well. So another couple of points. There's no situation in which all assumptions, where a given assumption is always appropriate. So let's say you're modeling a geothermal bore field, and you're trying to get some idea of the heat transfer that happens within that field. In some cases, you could make the simplifying assumption that, look, there's no water moving through this field. I can assume that it is completely dry, and I will solve my heat transfer equations with that assumption in mind. That may not be appropriate if you've moved your project then to some other location where there is an aquifer moving through there. It changes the dynamics of these things entirely. So you can imagine, as a software developer, sitting down and saying to yourself, all right, am I going to allow for water transfer through this, or am I going to not allow for water to flow through this? If I don't, I'm limiting what my end user will be able to do with the software. If I do, I'm forcing them to tell me a whole lot more information than may be necessary in most of their cases. So we have access to differing levels of assumptions. Now I'm sort of talking a bit more as a practitioner, as a user's perspective. You can just give up on one tool and use another one because tool A has something that you need it to have and tool B doesn't. Or, and I think we've probably all faced this scenario, you've got a number of assumptions built into the piece of software that you're using, a number of different options. Maybe there's a detailed model and a simplified model of some particular process that you can use. So I'm going to take the example of you've got a building, it's sitting on the ground. Okay? There's some energy transfer between the building and the ground. So what do? How do you want to account for that energy transfer? Well, the simplest thing you can do is just ignore it. Pretend that it's inconsequential. And there are probably a lot of situations in which that is exactly the case. Let's take the idea of a skyrise. You've got a skyrise which maybe has a basement, but the energy use of that skyrise is entirely dominated by what happens above the ground. The footprint of that building is relatively small in comparison to the rest of the surface area. So you might say, correctly so, I don't care about the ground transfer. It's just, it's not gonna matter. There's a method that ASHRAE published many, many years ago. It's been around for a long time. I don't want to get into the specifics of it, but the idea of it is that you sort of say, well, the ground kind of acts as a resistor, a thermal resistor between the building and the ambient, and they give you some guidelines as to how to come up with what that resistance should be. They give you guidelines, and so all you have to do is provide one value in order to implement this F-factor method. Give you some guidelines, but there's a lot of buildings. In fact, there's probably no building on the planet that actually conforms to those few cases for which ASHRAE gives you values. There are a dozen, if not more, ground coupling models available in between this F-factor method and something like a finite difference method where you're solving the problem with a sledgehammer. You're going to say, I've got a building, it's surrounded by some soil, and I'm going to break that soil up into lots and lots and lots of little chunks of soil, and I'm going to clobber it. I'm going to calculate the temperature of those chunks of soil at every hour, maybe even at every 15 minutes throughout my entire simulation. So again, you can see a great range of availability of assumptions. You may have a software tool that you're using for energy modeling that only gives you one particular option. You may be using a piece of software that gives you a bunch of different options. Again, it's up to the software developer to decide at the beginning of the process. It's up to the software developer to decide sort of what are the parameters of how we're going to deal with this assumption and all the other assumptions that go into creating an energy modeling tool. So in my experience, it has helped me to think of software tools on sort of a sliding scale. The more assumptions that the tool developer builds into the software, the quicker it is for the end user to implement the model. And I would give you the example, I don't know if anybody's ever used Target Finder. Target Finder is an online tool, and you essentially say, what is the square footage of my building? What is the basic energy use profile? It's a school, it's a hospital, it's a retail. And then you say what zip code it's in, and you push a button, and you get back how much energy that building is going to use in the course of a year. That's a really simple model. It's very fast to implement, and it has almost no flexibility. If you've got a building that is partly school, partly parking garage with a, you know, sort of industrial facility attached to it, you're not going to find that in there. On the other end of the spectrum are tools where the software developers have built in very few assumptions, and where you've got, as a user, lots and lots and lots of flexibility, but what you're going to pay for is implementation time. It's going to take you a long time to put together that building. So just to give you a couple of very simple examples, eQuest. Many of you may be familiar with this tool. It's freely available. And when you're designing the geometry in eQuest, you're faced with, you're presented with information like this. You've got a basic building footprint, and you can sort of slide zones around. But it's relatively simplistic. It's orthogonal. Architects never design buildings that are orthogonal, and engineers love them. A tool at the opposite end of the spectrum is one that I use a lot called TRNSYS. And there, this is sort of how you're faced with developing the geometry. You just get to draw the building. And this, you can imagine, takes a whole lot more time than what I showed you with eQuest. Now, I don't by any means want to disparage one tool or another. I used to have the opinion that all tools should trend towards the most flexible thing possible. And I really don't feel that way anymore. I really feel that the great advantage is to have tools available all along the way. Because there is a time and a place for dealing with complicated geometries, and there's a time and a place for actually getting an answer in some finite amount of time. Another spot within eQuest, you're presented with a few possibilities for what the HVAC system that you're going to meet the building's loads looks like. Okay? You can pick, I don't have anything. You can pick, I've got a furnace, I've got hot water. But if you've got something hybrid, that's not going to be available to you. They've built in more assumptions, and their assumptions cover a great majority of the sort of conventional building stock in the United States. Taking a look at what a TRNSYS system looks like, you're faced with a lot of individual components, down to the level of individual pumps, heat pumps, and pipes. This gives you an awful lot of flexibility. But you can imagine that it takes a pretty darn long time. You've got to go into each one of these and say, well, okay, there's a tank, but how big is it? What is the value of the insulation on it? How many inlets does it have? How many outlets does it have? A huge amount of flexibility. eQuest. These are two toys that I played with a lot as kids. Playmobil, you buy something and it is what it is. You've got some pieces. It's not particularly easy to expand upon what somebody else has come up with. It's got features and it has a scope. In this case, the scope of eQuest is really building energy modeling. You're not going to be able to do modeling of power transmission with eQuest. That's not within its scope. A lot of the tools that have more built-in assumptions have got predefined output reports. You run it, it gives you a huge amount of information, and it's up to you to sort of pick out that information that you need. But if there's something that's not there, there's very little chance that you can go and find it. And there's not much ability for you to add to the package. If it's not doing solar domestic hot water heating, there's not a way for you to go in and add solar domestic hot water heating to these less flexible, quicker turnaround type of tools. So I think of the more flexible longer turnaround tools as this model is never done. There's always something else that you could plug into it. There's always, some little doohickey that you could fit onto these bumps in the front and expand on either the complexity of the model or expand upon the content of the tool. So these ones, because somebody may be doing work on assessing the energy transfers within an anaerobic digester system, or they may be doing traffic flow, or they may be doing some other transient process. There tend to be, with this type of tool, far fewer output reports available that are canned and that you can just go and get. There's output, of course, but you have to sort of go and ask the tool for what it is you want to know out of it. And with some of them on the more flexible end, if there's not a model that represents whatever it is that you intend to model, say there's some newfangled piece of equipment out there. I ran into this a few years ago where we were doing a model of a natatorium, a building with a swimming pool in it. And they had the most complicated natatorium dehumidifier I have ever seen. This thing was unbelievable, the different modes of operation that it had. It could dehumidify and reject energy to the pool water. It could dehumidify and reject energy to the airstream to warm it back up. It could dump it outside. It could dump it here. It could dump it there. Whatever you could possibly imagine this piece of do. And fortunately, in this case, I was using TRNSYS and able to create a model and add it to the environment that allowed me to upon what it already was able to do. Any questions just thus far? So what I've tried to do up till here is sort of lay some groundwork for the different types of tools that are out there. Now, there are different kinds of projects, of course, out there as well. And projects don't always have the same goals, even though they're all energy modeling projects. And so I'm going to take a look in a little bit more detail at two projects that we did. One is this First Unitarian Society Meeting House, and the other one is a faculty office building at the University of Wisconsin. In some ways, these projects are very close to one another. They are literally, I don't have a good throwing arm, but I could probably get a rock from one to the other. They're literally right across the street from one another. In some ways, they have some of the similar goals. When we started out with these projects, this one, both of them had, and I have a slide on the other one later, but when we went into these projects, both of them had really aggressive goals for energy efficiency. They really wanted these buildings to be exemplary in an energy, in terms of their energy use. Both of them had lots of glass and lots of thermal mass for different reasons, but they boiled down to aesthetics. In one case, they were trying to follow along with a historic Frank Lloyd Wright design, and in the other case, that was just sort of how the aesthetic of the building turned out. Lots of glass and lots of thermal mass. So that brings up the issue of comfort. Those are high mass, high glass buildings tend to be harder to keep people comfortable. And both of them, as you could see from the previous slide, both of them were in Madison, Wisconsin, right across the street from each other. So they both have a summer climate that is hot and humid and a winter climate that is cold and pretty dry, although it can be humid of a different sort in the wintertime. And both of them had significant amounts of Western exposure. At that level, the similarities diminish significantly. So this Unitarian Meeting House had a significant number of rooms that were below grade, so the ground heat transfer was going to be an important aspect of whether this building was going to, of how much energy this building was going to use. The systems were very different. The Unitarian Meeting House building had a little bit of HVAC by means of air, meaning blowing hot air and blowing cold air into the space to keep it comfortable. But the large majority of the thermal loads were going to be taken up by radiantly heated floors and radiantly cooled floors. So we're talking about concrete floors that have piping in them, and it's kind of a no-brainer thinking about how to do hot radiant floors. Cold radiant floors can get you into trouble if condensation starts to become a concern, and it certainly was natural ventilation. So they wanted to be blowing comparatively humid air through the building and then decide, okay, we got to go over to cooling, and we're going to do that by cooling off this big concrete surface. So there were lots of issues as to, is this going to work, or are we going to be splashing through puddles on the floor of this building? This is a diagram just to sort of show you how unconventional this system was. The main sort of center point of this was a very large water source heat pump. It had, this is showing some other piece of equipment, but it ended up being a ground loop. And you can see that you've got this main heat pump, which is either providing you with hot water in the wintertime or cold water in the summertime. And it's feeding hot water coils in 3 different air handlers and in an energy recovery ventilator, and it's also running a bunch of radiant floors. It's a very unconventional system. And there are also some heat pumps that were, these are air to water heat pumps, and there were questions within this project as to whether these air to water heat pumps, which were serving a set of classrooms within the building, whether these air to water heat pumps should be on the source side of the ground loop, or whether in fact it should be on the other side. So we did a whole bunch of work reconfiguring the system. Now, take a step back and remember that diagram that I showed, sort of indicating how you define systems in eQuest and indicating how you define systems in TRNSYS. It's probably not a big stretch of the imagination to say, okay, I get it. In certain cases, that flexibility is a big advantage. And it certainly was in this case. So the other aspect of this project, however, was that we were pretty certain that we were going to manage to make a energy efficient building. We wanted to know, of course, how much energy is this building going to consume, but at the end of the day, it's pretty easy to make a zero net energy building, right? Unless, of course, you care whether people are comfortable in the building. And that was much, much, much more the issue in this particular project than was the energy use. So we spent a good bit of time, and have done so on other projects, trying to find the metric that really conveyed the results of the model when SCADs and pages of numbers weren't going to cut it. And we came up with some interesting things, and I just have a couple of slides here showing a few of them. One of the concerns was that because we had this below grade zones and some above grade zones, whether this radiant floor that we were considering was going to make for surface temperatures to be uncomfortably hot, radiant temperatures to be uncomfortably hot. So one of the metrics that we looked at was the surface temperature of these floors on a minute by minute, hour by hour basis throughout the entire year. Again, the flexibility of a tool that doesn't give you command or canned output reports was an advantage in this particular case. Another thing that we looked at was the difference in performance between using an energy recovery ventilator, a mechanical device, and using earth duct. It's a more passive device. And the idea of an earth duct, if you haven't run across them, is you've got a bunch of tubes buried in the ground, and you're drawing your building's outdoor air down through the ground and then up into the building. The idea is, the hope is, in the wintertime, you're going to pick up a little bit of energy because the ground is warmer than the air if you go deep enough, and if below the frost line. And in the summertime, you're going to be able to draw that air in and pre-cool. So it's a passive device. It uses only fan power. And while this one basically uses only fan power too, there are filters here that tend to drive up the fan pressure and cause you to have a lot more, these things have a lot more power than require a lot more than these do. And again, we struggled and struggled and struggled to figure out what is the way that we can convey how these two devices are performing, except from saying, well, this one uses energy, this much energy, and that one uses that much energy. That wasn't really the primary concern. And so this is essentially a plot here. In the dark blue on both of these plots, what you're looking at is ambient conditions in Madison, Wisconsin. And then what you're looking at in light blue on this one is the conditions of air coming out of an energy recovery ventilator. So you can see from a metric like this that, in fact, the energy recovery ventilator is doing a great job of heating in the wintertime. All these dark blue mess gets moved way, way, way up, and we don't have to deal with it. It doesn't do too terribly much for us in the summertime in terms of dehumidification and cooling. However, if you look at an earth duct, the situation is quite different. Again, dark blue is the ambient conditions. Light yellow and pink are two different configurations of earth duct, but what's important here is that the primary benefit of this thing is in the cooling and dehumidification. And yeah, there's a little bit of heating benefit, but really it's not as significant. Again, the result here is not particularly relevant to what we're talking about. What's more relevant is the tool's ability to present information beyond numbers and numbers and numbers and numbers. I realize we're all, many of us engineers in here, and numbers is what we like, but communicating the impact of those numbers can sometimes be a bit of a challenge. Okay, so what went right here? The goals of the project and the capabilities of the software tool were very well matched with each other in this particular case. We had also benefited from the fact that the goals of the project didn't change halfway through the project. Have you ever been on such a project? It actually can happen once in a while. And this was a benefit. This is one of the reasons why it worked. The main reason was that the flexibility, the main reason why this project worked well is that the flexibility that the tool we were using was actually an asset in this case. We're using the right tool for the job. So change gears a little bit to the building across the street. It's this one right here. It's part of a much larger hospital complex. Again, they had great aggressive goals for how much energy they wanted this building to use. They had designed a building that had a comparatively large amount of glass and rather a lot of mass inside it. And again, it's in Madison, Wisconsin, so the same kind of concerns about the climate. Some things that were very different were that in this case, eventually they ended up going with a pretty conventional VAV air handling system. That's not where they started out, but that's where they ended up in this particular. To have some comfort considerations that were going to need to be dealt with. But they ended up with a lot of closed offices and really very much wiped out all of the energy use that the building was going to see. So the skin didn't matter, nothing mattered. There was this massive use of power for the servers down in this data center, and it became quite challenging, any energy efficiency in this building, apart from trying to do some heat recovery off the data center. So in this case, I mentioned one of the assets in the Unitarian case was that the project goals didn't change. The project parameters didn't change all that much throughout the course of the project. But some of the HVAC stuff did change. I mean, originally they were talking about radiant floors and minimal glass and open office plans, and they definitely shifted on that over the course of the project. The only metric that they ended up caring about were the numbers, where this building is going to use X kilowatt hours per year and so many therms of gas, and the comparison building is going to use more. Okay? Again, the numbers are pretty irrelevant. But you can see, perhaps in here, that I didn't actually look at these numbers, but this receptacle equipment, this is the data center there, where they're the same between the two, and so we were comparatively limited in how much, in where we could get savings in the rest of the building, since it had this massive power use down in the basement. So what went wrong in this project? It was a disaster. There was much screaming and yelling and gnashing of teeth. So what went wrong? In part, there was in part it was because the goals of the project started out one place. We're going to make a really energy efficient building, and ended up where there were a lot of concerns that changed the nature of the building that hadn't been addressed early on. It's a bit of a vague statement, but what really happened was that when the project began, the decision-making criteria was supposed to be energy use. But it turned out that the decision-making criteria was, we got to give these professors what they want. And they don't want big open office plans. And they don't want natural ventilation. And they don't want minimal views of the outside. They wanted other things. And there's no right or wrong about that. But I think one of the things that didn't go right about this project was that the decision-making criteria was unclear. And there were factors at work. And I think that is a good takeaway for this whole subject, which is that if you're not clear up front about not necessarily who is making decisions, but what your criteria for evaluating options is going to be. Is it going to be energy, or is it going to be something else? At some point, I think the culpability on our part in this was that the flexibility of the tool that we were using was a huge disadvantage. We're dragging out pumps and fans, and they're changing the entire nature of the HVAC system quickly. They can change it much more quickly than we can catch up with it. And so we infuriated them by being so slow to respond. We should have, in retrospect, we should have cut bait and used some different energy modeling tool. But the world not being a perfect place, we were too deep into it, and we didn't see that that was the problem until it was way too late to actually do anything about it. Oops. All right, so those were two projects that went particularly well and particularly poorly. I also wanted to bring up a couple of other, those were both, I should say, those were both new buildings that were being designed, and there was a great deal of leeway as to what we were actually doing with them. There are other kinds of energy modeling projects, right? There's all sorts of energy modeling projects out there. There's these measurement and verification projects. Are systems and buildings operating the way that we think they ought to be, or are they not? Can we find fault with them through the use of energy modeling? Or can we improve upon their design through the use of energy modeling? So I wanted to mention that a little bit pretty briefly here. I think one of the easy initial assumptions that one can make about these measurement and verification projects is that you do want the flexibility. You want all sorts of flexibility within your data modeling or within your modeling tool in order to be able to make it match the reality of some data that you've measured. But I would say that's not always true for a couple of reasons. Remember that along with flexibility comes a demand for a hugely increased amount of information. So if you're facing a situation where you've got a building and you've got only the gas use of the building and the electricity use of the building to look at, you don't have very many metrics. You don't know anything about the weather that the building was facing during the time period. You don't have any sub-hourly, you don't have any sub-metering, so you don't know how much of this was lighting, how much of this was HVAC. If you don't have a lot of data available, then the flexibility may actually be a disadvantage to you. If the tool that you're using demands that you tell it all these things and you don't have that level of specificity, that level of fidelity in the data that you're using, there's not an advantage to the flexibility, and all you're going to end up with is too many knobs to turn. This also brings up a case, a point here, which is with these more flexible tools, you have hundreds, if not thousands, of little knobs that you can turn, many of which have similar. So what the heck do I mean by that? So let's say you're dealing with a building, and one of the things that you almost never know about a building is how leaky is it? How much air is oozing in from outside that you can't control? There's no way to really measure that. So you can adjust the infiltration rate into the building, but there are lots and lots and lots of other things that would have the same end result. So what if your insulation isn't quite what you think it is? Should you modify the infiltration rate, or should you modify the amount of insulation that you've got on your walls, the effective thermal properties of the infiltration, or the insulation? You're asked to provide the insulation density and thermal conductivity, and those things are published based on lab tests, but what are they really in the field? There are so many ways that you can fiddle around with the inputs, and oftentimes if you've got a tool that is highly flexible, you've got too many knobs and not enough gauges. Now, that's not always the case. Sometimes there are cases which you have an appropriate amount of data and you have an appropriate amount of flexibility. Again, this is a bit of a two-way street, and I think here the takeaway I would like to leave you with on this particular subject of measurement and verification, I think it bleeds over into the others as well, is look really carefully at why you're doing this measurement and verification exercise. Because oftentimes, I think anybody who has done energy modeling gets more questions out of the model than they get answers. Sure, they get some answers, and they get some questions about those answers, and they want to go off on a tangent, and well, I see you're smiling, you've been in this situation. It's a rabbit hole, and it's a really fun rabbit hole to go down. And at some point, you sort of pull yourself up and you say, whoa, wait a second. You know, the third order polynomial of this particular fan power curve really doesn't matter all that much. What we're trying to do is have a model that acts more or less like a physical process. More or less like a physical process. So I think that early on, defining why you're doing this measurement and verification is paramount in trying to select a tool that's going to be an appropriate tool for what you're trying to do. We've been doing some work recently on energy efficiency in domestic and hot water use, service hot water use. And the end goal of this actually is to look at some differences in not the energy use directly, but in the water use itself. There are some newer products out on the market that can dramatically reduce water waste. And what with water waste being a going concern, particularly in California, this has come up. But here, what you're looking at is a plot of, I think these are in 15-second intervals, of the temperature at the top of a hot water tank and then at the bottom of a hot water tank. It's a bit hard to see, but there's a gray line and a green line here that overlap each other pretty darn well. Over here, you can start to see a little bit more separation. And then up at the top of the tank, you've got a blue line and a red line, which are the measured and simulated temperatures near the top of this tank. This is a pretty conventional recirculation loop. And I bring it up because this happens to be a case where we had lots and lots of data on a very well-documented lab test system. This had it was a domestic, I think it's a 120-gallon domestic water heater, and about a 400-foot recirc loop. Everything was measured on this thing. We had tons and tons and tons of data because it was a lab setup. And so the tool that we were using, again, TRNSYS, happened to be the right one for this particular case because we could make use of all that information. That was the kind of information that our software tool needed to begin with. So it was beneficial, certainly, to have access to it. I also wanted to mention central plants a little bit. Central plants are often, well, they're often a challenge to model for a number of reasons. One is that if you go to one central plant and then go to a different central plant, there's not going to be much, there's often not much similarity between the two. If you go to a house that is in Boise that is heated by a gas furnace, and then you go to one in Madison, Wisconsin, those two systems are going to be identical. But if you go to, say, the campus power plant here that provides, is it steam? Yeah. If you go to the campus power plant that provides steam on this campus and at the one at UW, you're willing to bet there's absolutely no similarity between those two. Existing plants, for one thing, have often been built and expanded over time. The first chillers were put in there in 1970, and then they needed some more capacity, so they put in a few more, and they're a different model and a different size, and then they put in some more in the 90s, and then they took out that first one and replaced it with something else. And then somebody got the bright idea that they got a grant for an absorption chiller, and so that got stuck in there. These things evolve, and so oftentimes it is hard to model them with a tool that is more broad brush, that offers you less flexibility. Oftentimes too, I put up here that their control sequences are not well documented. What that means is there's some old codger who works in that central plant who knows exactly how the thing works, and only that person can explain, well, you know, when this thing starts glowing red hot, I do this, and you know, when it, you know, poor documentation, if it's documented at all, and it's probably not running the way it's documented to run in the first place. New plants, there can be some more consistency or some less of these challenges, but a lot of times in the plants that we have been faced with, you'll find a situation where they're planning on a certain number of chillers, and those chillers have a built-in sequence of operations as to how those things function. And then they'll get a heat source that has its own built-in set of rules as to how it should be operated. There's oftentimes mismatch between those two things. And if you just hook them up together, they'll operate, but they're not going to be operating at either one's most efficient point. And when you've got a lot of these different pieces kicking around in your system, being able to do a system-wide model of it, as opposed to taking the manufacturer's word on this is the chiller performance and this is the boiler performance and this is the tower performance, and we're going to get, you're going to get some combination of those performances instead of, and so instead of the sum of them. We often find that one of the places where we have been able to be helpful on these kinds of projects is to model the whole thing and get an idea of, okay, I know that the manufacturer said these chillers should be loaded like this and unloaded like that, but because you've got this other part of your system over here, chances are that if you load and unload these things a little bit differently, they're going to perform better system-wide. Okay? So in what I have experienced, the flexibility here is a great asset. I have not found a situation where we have not benefited from the flexibility of the tool. This is a bit of a eye crosser, but it's a central plant that we were working on some time ago. It's got a set of 3 engine generators. So they're providing electricity to a small campus of buildings using natural gas-fired generator sets. They've got waste heat off that. They knew they were going to have waste heat off that. So the idea was, what can we do to make use of this waste heat? Well, the obvious idea is absorption chillers. And so they've got down here a pair of absorption chillers. And the idea, generally speaking, is to take most of the stack exhaust off of these things and pass it into a storage loop, run this storage, and then when they could, run cooling from these absorption chillers, and when they didn't have enough to run these absorption chillers, hot water to run the absorption chillers, then they've got some more traditional electric chillers running in the background that they can ramp up to meet their cooling load for this campus of buildings. And then also, if there was excess hot water available based on how they were running these generators, then that could be used to supplement a boiler loop here that was providing heating to campus buildings. And there's a lot of other little things here too, and I have removed the cooling tower loop from this diagram. There was a cooling tower. There is a cooling tower loop in there as well. But I took it out just for the sake of clarity. But this design here evolved enormously over the course of the project. It's a bit of a funny situation, because when I was brought into the project, They were at, I think they said they were at something like 75% design development. They had blueprints, they had drawings, they had everything. The only thing they didn't have was the sequence of controls written down for the entire system. By the time we did our lab on this, which is what you're looking at, probably 8 months later, the last design I got was literally a scan of a napkin that had a sketch on it. And that, of course, then got developed once more. But there were so many issues about, well, how should we run these things? Should these things be run to meet an electricity load, or should they be run at some other efficiency point? And the campus should buy electricity at times and sell electricity at times. Should we run these things in order to make waste heat, in order to fire these absorption chillers? Or should we run these things at some very low baseline and not meet our electricity needs, use these things minimally, but really what these things are here for is helping us save energy in the hot water loop? There are a lot of really fascinating lessons learned from this. Again, the flexibility was really key. All right, some takeaways. My title here was eHarmony, between projects and modeling tools. There's a lot to be said for the compatibility of those two things, right? You're going to get a bad situation if the expectations of the one and the capabilities of the other don't fit well with each other. And I think one of the ways of doing that is from the outset, to the best of your ability. And I realize that this is the best of all possible worlds. To the best of our ability, we should be very persistent in setting the goals for the energy modeling. I was dealing this morning with a situation where we were brought on board to do a lead energy model of a building. Fine. We're working on the lead energy model, and somebody says, can you give me the model? We need to check code compliance. That's a very different energy model than a lead energy model. You asked me for an elephant originally. I'm building an elephant. You've now asked me for a rhinoceros. This rhinoceros is going to have a trunk and 2 big ears. And there's not much that I can do about that. I'm a little worried that this is going to go down the faculty office building route, because I'm going to have to explain that, yes, I'm building an energy model. No, it's not an energy model for compliance. I see some of you nodding. You get that. That's rare, or more rare than it would be, than would be ideal. The decision-making criteria, I think, is also a very important point. When design teams get together, there are many, many, many intentions. And figuring out whose intentions are going to be the ones that eventually rule the day is a really important exercise to go through. I think one of the things that really went poorly in that Centennial project was that the design team was of the understanding that decisions were going to be made based on energy. So we moved down a path of using an energy modeling tool that could help make those decisions. It turned out that there were many other factors at play that had nothing to do with energy. And so the tail that we were was not being wagged by the dog that we had anything to do with. This is a particular soapbox that I get up on a lot, and it comes from my software development end of things. The more you know, I think, about the underlying algorithms of whatever software tool you're using. If you're using a tool that is extremely, extremely inflexible but very quick, if that's what suits your type of project, that's great. The more you understand about the assumptions that it's making, I think the better off you are. I liken it to if you're skating on thin ice, if you're skating on ice and you know how thin the ice is, you may still fall in. But if you know just how thin the ice is, you can push the boundaries a little bit more. You can, if you really understand what the simulation is doing, or the tool is doing, how it's coming up with that value of energy use. Where does that come from? If you understand that, then I think you can push that tool a little farther beyond the boundaries. If you don't understand that stuff, you've got to stay a little bit more conservative. You've got to stay a little bit farther away from those edges. It's worth having some flexibility or familiarity with other energy modeling tools, but that's a bit more difficult. I mean, we're all limited in how much we can know about the tools that we use. And unfortunately, I don't think that there will be a day where you can describe your project, or at least I have no intentions of there being a day when you can describe your project into some social media thing and it will tell you which software tool you ought to use. But, I don't know. Maybe somebody smarter than I can do that. That's all. Does anybody have any questions or comments?
So, as far as the balance between how flexible versus how quick. As far as the balance goes between how flexible you want the software to be versus how quick you'd like it to perform analysis for you. Seen some software tools will have like wizards or kind of different levels of default values that are assumed. Are you seeing or expecting a trend more towards that? Let's get some kind of intermediate wizard kinds of things in here, or more siloed, different, complete software tools?
That's a very good question. I'm speaking rather personally here. I don't like wizards because I find that with the type of modeling I do, if I don't build that thing up from the ground and understand each piece of it, at some point I'm going to get some behavior out of it that I don't understand and can't explain. So I'm not a huge fan of wizards because of those default values. You never quite know what they're selecting. And I say that, but there are many engineering projects where you're at the schematic design level. And those wizards are very good for those purposes, where, you know what, I don't know what the coefficient of performance of this thing is going to be. I'm just going to put 3 in for now, and then I'll come back to it. And the lines are a lot more blurry than I have made them out to be. You can be more flexible with eQuest than those slides suggest. And you can be less flexible with TRNSYS than those slides suggest. So the lines are gray. But I am also not a huge fan of the push towards interoperability and data models that can be shared between software tools. I see an advantage in there being a great deal of diversity of energy modeling tools out there, even if it means that you have to start over again. Now, interoperability, data model sharing between, say, building geometry, fine. But I don't wish for a day when I can take my eQuest model and just drag it onto TRNSYS and drop it there. Because I think that those two languages are so different from one another, and the intentions of those two softwares are so different from one another, that I think you'd be better served to, if you got to start over and do something more, if you need more flexibility, start over and do it from scratch so that you really understand what's going on. Again, that's just my particular experience, and I will be the first to admit that I live in one of the strangest, smallest backwaters of energy modeling that exists. And not often that you see central plants that look like that. Any other questions? Or? Hang on one sec for the microphone. Yeah.
Tell us a little bit more about your interface. Is it graphical? Is it command line scripting? What do you use to generate a model? I saw SketchUp in there. Right.
So building geometry is actually generated using there's an Open Studio legacy. There's a legacy Open Studio, and then there's the more recent Open Studio. So we use something that is built onto the legacy Open Studio for building geometry. The interface for TRNSYS itself is very much drag components out from a list of components. So you have folders that say pumps, and you can go and select from, I've got a constant speed pump, I've got a variable speed pump, I've got a 2-speed pump, I've got a whatever it happens to be. You drag that thing out, you double click on it, you set up its staging points, or you set up whatever it's asking you for, and then you drag out the pipe to which it's connected, and then you graphically connect information flow, really down at the minute level. But yeah, there is a graphical interface. Underneath the graphical interface, there is a text file. And it's interesting, my colleague just got back from the SimBuild conference and said, everybody is talking about scripting now. And so scripting and getting at those text files seems to be the thing now instead of what it was 5 years ago, which is interfaces, interfaces, interfaces.
My question has to do with follow-ups with the clients. Were they, either one of them, happy with the results after you created the model? Is it something they were expecting, or was it not what they were expecting?
In both of those two cases, the energy efficiency, the quantitative result was quite satisfactory to both clients. It was the process that was very unsatisfactory to one and very satisfactory to the other. So, but you bring up a very interesting point, which is that you often get into situations where the energy modeling does not give people the answer that they were hoping for. And that is another can of worms. It's a very difficult thing to manage. Because we used to joke that we are energy debunkers. We have brought more bad news to clients that this idea that they've got just isn't going to save the world in the way that they wanted it to. We've been buzzkills more often than not. And knowing how to bring that along through and present that information is an important skill. And again, I think it also does speak to the flexibility issue. If you've got a tool where you can dig deep and understand why it's not working the way they hoped it would work, you can say, look, right here, if you look at these temperatures and these flow rates, right here at this point, you know, in your original design, you thought that this particular transient thing was going to happen 5% of the time, but in fact, this transient thing where nothing's being efficient is happening 80% of the time. Then you've got, I don't want to say more ammunition, but you've got a deeper well from which you can draw the reasons for a consequence. If you're just pushing a button, letting it go, and getting a 18%, 17%, it becomes very difficult to know where those two final numbers came from. We've had some questions. You guys are behind here on this side of the room. Yeah, please. Here, hang on.
I've heard that you have a logging for radiance for lighting simulations in TRNSYS. Can you explain a little bit about that and how it works?
I would like to. I'm afraid I have no idea. So TRNSYS is developed by 3 different entities. Our entity deals with sort of the components, the equipment, the hardcore HVAC stuff. We have some colleagues in Germany who deal with the building, and it is they who have been working on this plugin for daylighting and the coupling with radiance. So I'm afraid I don't know anything about that. It's due out in the next version of TRNSYS, and I have yet to see it, and I think I'm eventually going to have to learn something about daylighting. Anything else? Thank you all sincerely for coming. This has been a really great honor to be asked to do this, and I deeply appreciate it, and I thank you for your time. And by all means, if you think of a question sometime later, I would encourage you all to be in touch. I would very much enjoy that. These 2 projects are, in the 20 years that I have been doing this, the only 2 that have been in Madison, Wisconsin. So everything that I do is elsewhere.
Thank you. And can't offer you the opportunity to do modeling on it, but we do have a license, a single license of TRNSYS. If you're just interested in poking around, happy to let you guys fire that up. And since I know it's